This is a driverless chip, and a while ago I bought a couple of these, and then I misplaced them, and a few of you were asking about them, so I thought, okay, right, it's time to explore these. So I ordered a couple more. The other ones will turn up. I wonder if they're going to be the same type. But these are the new ones that have just arrived, and they were extraordinarily cheap. Now, I'm just going to zoom out here so you can appreciate the merits of a driverless chip. You see, here's a driverless chip in a floodlight. It's just the LED. And that's as opposed to the high-power LED and the driver. And that's going to save a lot of money and time in manufacturing, because when you remove these components, that's not just a chunk of weight, that's removing all this circuitry as well, that's inside this driver. So it makes things a lot cheaper. However, there is a slight drawback, as I'll mention later. Now, I got these LEDs from a supplier called 2012 Top Deal, but I have to say, I'm kind of suspicious because they're too cheap. They're just so cheap that you're thinking, is there a problem here? Are these the prototypes? Are these going to fail? Because at the moment, mine costs slightly more, but at the moment, the current listing offers 20, 30 and 50 watt versions. And they all cost the same price, which is $1.69 or £1.39, which just seems that, it just seems too low. When I first saw these, let's take a look at this picture of one. I mean, I don't really need a big picture of one since I can zoom in, but here's a big picture of one. And when you look at them, you can see there's clearly a bit of direct fire, some other components in here, and then a stack of these chips. And the power of the LED dictates how many of those chips there are. So in this 20 watt LED, there's just one chip, or so I thought. And in the 50 watt LED, there's 4 chips. And this is the 50 watt one. And I was looking at all these dots underneath and thinking, this reminds me an awful lot of these lights here, which have the array of LEDs, multi-chip LEDs, and they were using CYT 3000 drivers. And the interesting thing about the CYT 3000 drivers is that as the main sine wave, the rectified main sine wave, rises up and down, it switched in groups of the LEDs to actually ride the sine waves, so that, at the bottom, when the voltage was low, it would switch in a small number of LEDs, and as the voltage went hard, it would switch in more until it sort of current regulated at the top. And I wasn't overly enamoured because, as you can see in this one, there is a bit of a skid mark, and the CYT chips seem to have a bit of a history of just going bang and blowing LEDs, and I thought, oh, maybe that's why these LEDs were so cheap. So I peeled off the covering, and I was wrong. The chip inside is where is it? It's a bright power, which is a good start. It's a bright power. I've misplaced that bit of paperwork. There it is. It's a BP 5132H. And this is it's actually very similar to other chips. The SM2082, there's another one as well. Hold on. SM2082 and the CYT1000A. And both of these are dual current regulators. Each one contains 2 independent current regulators inside that you program with a resistor, and it limits the current almost like a variable resistor, but with the extra feature that if it gets too hot, it will start regulating the current down itself. And these are used in LED lamps like this, these filament lamps. And if you think about it, most of these LED filament lamps contain approximately 35 or so chips in each filament. And in the case of the UK ones, where you've got 240 volt supply, they then run 2 of those filament sets in this case, there's 6 filaments in this lamp, and so they run 3 in parallel in series with another 3 in parallel to give a combined number of 70 chips. And when I looked closer at this LED, I put this one into the case, and I have to say that this was an issue. Soldering onto these, I put it in and then thought I've just soldered the wires on. No, that didn't happen. It's the same old story that because this is an aluminium substrate PCB, it's got a thin shim of fiberglass on the front of aluminium. Because of that, it sucks heat away from the solder joints. And the only way I could actually solder this was to lift it out, put it on cardboard, and then heat it up in general, and then use a slightly beefier soldering iron than normal to actually just take ages to flow, to heat those up and then put these connections on. So if you want to solder onto these, you'll need a really incredibly beefy soldering iron because you're basically soldering onto a heatsink. However, I put this 20 watt one in and I powered it up, and I will power this one up later. I powered it up and it was really dazzlingly bright, so I put a couple of resistors in series to deliberately limit the current until I could see the LEDs and take a photo of them. And the resistors I put in, let's just make sure this is tightly focused, yes it is. The resistors I put in ended up, I had to put two 1 meg ohm resistors in series in the mains just to get them down to the point you could actually get a picture of the LEDs. And part of that was because of the flicker, and that is where we have a problem here, because there isn't really any particular smoothing at all, other than a small capacitor which is mainly for the circuitry itself. But I got my picture and it shows that there are alternatively 78787, and then there's a sort of dividing line, then there's 78787 again, almost like two blocks, as if perhaps these are designed to be operated in parallel on 120 volt but in series on 240 volt. So the total number of LEDs is about 74 LEDs. And then you think back to that, that's roughly the equivalent of those LEDs in, you know, the two filaments in series with the 37 LEDs per filament. And I've seen these chips, these current regulating chips being used in these LED filament lamps, and all they do is they act like a variable resistor in series with that string of LEDs. And there's a slight downside to that, because ultimately that's what's happening here. And where's my notepad? Where's my notepad? Where's my notepad? What that means is that when you've got the main sine wave, which is full wave rectified through that rectifier, then you end up with a sine wave rectified, but the LEDs aren't conductive for the whole duration of that. Typically, we can work this out. If I bring the calculator in, typically the forward voltage of the LEDs will start conducting is around about 2.5 volts times, and as far as I can see, all these LEDs are in series, 74 equals about 185 volts. So if we base this on the fact that this is to, say, 30 volt RMS, we'll go with the European route, that's going to be about 330 volts-ish. 280 volts is going to be sort of down here sort of region, which means ultimately the LEDs are going to be lit for this area here in each half of the sine wave, the rectified sine wave. And that does unfortunately mean that for this area here, they're flickering. You know, they're out, you know, on, off, on, off. It really is a strong flicker that shows up in the camera. I'm pretty sure it will show up in the camera while we're filming it. Let's, do we check that now, or do I, no, let's finish what I was talking about before. That's the best bit. Honestly, this has been a really enjoyable evening, you know, working out how these work. For a start, I thought it was pretty odd that the 20 watt LED seemed to have one chip, the 30 watt LED seemed to have two, and then the 50 watt seemed to have four. I thought it was quite odd until I discovered that this chip over here is another of these chips, these current regulating chips. And as far as I can see, they're all just wired in parallel and act independently as effectively having a resistor in series of these LEDs. And the reason they're doing that is just to get the sheer power output from these. So in the case of these arrangements here, it appears to be the same array of LEDs. I don't know if the 50 watt one has larger chips or if it's just standard. I suppose it would be reasonable enough just to make it standard. But for every 10 watts, they're using one of these chips. And that means the current is going to be in the region of 50 milliamps roughly per chip, I think. Just under 50 milliamps. And the manufacturer recommends about 40 milliamps. Sort of typical current. I don't know if they're using both the regulator sections in these or just one. The schematic that's given with this is odd. I don't know why they're doing this. They refer to this as a typical application, but they only show the LEDs going through one side of the circuitry. This chip is effectively two of these current regulators in one, and they're showing this erroneous resistor with its current sense resistor, and I'm not sure why they're doing that. Is this just to provide maybe a slight current flow in the other, in the area of the sine wave that the LED isn't lit, just to cheat power factor? I'm not really sure. Power factor is extremely good in the sense that the current does match the voltage, but because it comes up as a good power factor, but as I say, it's not perfect. An ideal power factor would show the sine wave with the current and the voltage absolutely matching, but this is a lot closer than you'll get with capacitive droppers or the switch mode power supplies. So let's take a look at one of the LEDs. So I'm going to power this LED up, and this is where it could get really flickery. I'll power this LED up. It will probably swamp the camera because the exposure is locked. I've got a power meter here which is going to look super flickery, as they always do, because it's got a multiplexed LED display. I may have to adjust the settings for, well, I may have to adjust the settings full stop. So let's power this up. I've not got any heatsink compound in the back of this, and that's for a reason. I wanted it to overheat deliberately. I wanted to see it current regulate, but it didn't. Right, okay, we've got super current, super. Let's turn this over. It's flickering too much. Sorry. That's the reality of these driverless LEDs. They flicker like hell. Okay, so let's take a look at the readings here. Let's bring this up and focus on this and lock that off momentarily. So what we've got is about 100 milliamps, 50 milliamps per chip. 241 volts at the moment, 50 hertz. It's showing 25 watts here. And the power factor is a really pretty good 0.9. That's pretty good for a power factor. Let's unlock this and go back down, and let's focus back down to a nice sensible level. Let's focus back down that. So this got very hot, as you'd expect, but not excessively hot. I'm not sure I trust. I think that if you get a 20 watt one of these and a 50 watt one of these, the 50 watt one is not going to last as long because it looks like the LED chips are being driven quite hard. However, I took a thermal imaging shot of this unit operating with a 20 watt LED, and it showed the hottest items were actually the chips versus the LEDs. The LEDs and the non-thermally coupled plate still screwed onto this heatsink, and the heatsink does get pretty hot. The LEDs were getting up to about 80 degrees Celsius, but the chips were going up to 92 degrees, but that's well below the point they'll start thermally regulating. So to be honest, the 20 watt one actually is pretty good, even without the heatsink compound. That's extraordinary. But as I say, it flickers. Yeah, we don't like the flicker. What else can I say about these? Well, I kind of bought these to go into in more detail, so I'm now going to start scraping all this stuff off. So let's get rid of everything else here, that's particularly the flickery bits. Let's move it all off the bench and start exploring this. So I'm going to zoom down onto this so we can actually see what's happening a little bit closer. Double check it is completely focused. Yes, it is completely focused. And then I'm going to get a big chib and get into this. So let's get a knife and start scraping. So looking at this arrangement here, it looks like these bright power chips, and also I have to say bright power. I quite like the fact it's bright power. Let's just change the exposure a wee bit. No, it's fine. No, it's not. No, it's fine. I'm quite happy that it's bright power because bright power are one of the industry leaders in these chips, in sort of LED drivers. So what we have here is we've got the 5 bright power chips. This is a bright power chip 2. We've got the little capacitor which is associated with the schematic of the bright power. Hold on, schematic again. That'll be that little capacitor there. We have, under here, we've got the sense resistors. There's also a component here. The neutral seems to go straight to the rectifier. The live comes in and goes via this component, which is either a fuse or an inrush limiting resistor perhaps, and then it goes to the bridge rectifier. Let's go down there and see if we can find out what this is. So let's dig in through the silicon goo. And there's silicon goo everywhere. I guess they're just ultimately trying to make the thing as waterproof as possible, which is reasonable enough. That's a good move. If this starts turning out to a wee bit too tricky to take to bits in a controlled manner, because the silicon, the worst thing about the silicon is it is kind of like a bit rubbery. Well, yeah, because it's silicon rubber, basically. And sometimes it doesn't peel off as easily as it could. So what have we got here? It looks like a resistor. It might be a fusible resistor, or a resistor being used as a fuse anyway. Right, so what have we got? That just says 000. Is that just a link? It looks like it might have been intended to be a fusible resistor, but it's just a link. Okay, let's go in further. Let's start digging down in here. So there's other components under here. I'm guessing that fundamentally, most of the components under here are going to be a sense resistor for that chip. And that's more or less going to be it. This could end badly. This is a new knife, by the way, so I just want you to know that it's very, very sharp. It's also very stylish. It's got this amazing action. I just thought I'd mention that for no good reason at all. Yeah. There's a set of harder silicon here, which is the bit that's been used as the outline so they can then pour this silicon in. Then the softer silicon that's covering the components. I really think that all we're getting here, by the look of it, is one resistor. Can I get a value on that resistor? Can I see that yet? Is it uncovered enough? No, I can't. Oh, it's not quite uncovered enough. If I get something else I can actually claw at this silicon with. It's all just a little bit tight. Now, I see at the other side there's also the little resistors that are hiding under here. And I'm guessing that ultimately those are just going to be the same. Let's just, I'm going to end up destroying this, and it might seem a terrible thing to destroy a perfectly good high power driverless LED, but to be honest, it's better me destroying mine than you destroying yours. Now, once you know what's inside, you'll be able to make an educated decision. Yeah, these are just, it looks to all intents and purposes to be perhaps one current sense resistor per device. Not quite making that out. So I'm probably going to pause, and I'm going to actually start cutting in and removing some of the, the silicon in general up here. Oh, let's just do it right now. Let's see if we can peel this back. Is it going to come off intact? I'm not sure it is. I want to see what's underneath this. I'm going to probably rip all the chips off, the LED chips themselves. Oh, yeah, I'm making scrunchy noises. This LED is a dead LED now. It is never going to work again. Tempting as it is to actually power it up and see what happens. As soon as you've broken the circuit of the LEDs, they're as good as dead. Right, I'm going to pause momentarily to work on this, and then we'll take a closer look afterwards. Quick jump cut because it was going on a bit too long. So to cut a long story short, I completely shredded it. I took it completely to bits. So let's take a look at the arrangement here. The power comes in live, comes through this 0 ohm link, which I'm guessing maybe they've designed that to have either a resistor in it for current limiting, inrush limiting, or but there's no capacitor as such. I mean, there's this little capacitor here, but it's for a completely different part of the circuit. But maybe it's just being used as basically a fusible link. So it comes through that, and neutral goes to the other end of the bridge rectifier, and you get the DC out. So the positive goes straight up to LEDs, and it actually then starts snaking its way down. And it doesn't just go in a straight row backwards and forwards. It actually is designed to zigzag up and down on each row to allow all the positive end of the chips to be at the same side. So the pick and place machine that's putting these chips on before they get bonded across, it can put them all in the same orientation. There's also the facility to put 2 in parallel in each position, but that wasn't used in this case. Even though it was the 50-watt LED, it did not have the parallel ones. So it zigzags down, and there is that oddity here. I'm not sure if this is designed for bridging out. Maybe it's designed to facilitate another design. I should actually, I could have ordered a 120-volt LED, but I didn't. I didn't realise I'd want to actually look for that. But anyway, this is the 240-volt LED. It's got the 74 LEDs, 74 LEDs that zigzag down and they come to the bottom, and then all these chips are just effectively ganged in parallel. And this is where I bring in my little doodle, because here's a schematic of the LED. It's quite odd to see a schematic of the inside of an LED. Well, it's an LED module, I suppose, and it differs greatly from the manufacturer's recommended sort of outline, so to speak. Whereas the manufacturer's design, the datasheet shows the positive going through the LEDs and a capacitor being across the LEDs. This does not have a capacitor across the LEDs, however, it does have a capacitor across the chip. And I'm guessing that ultimately the reason for that is just for stability more than anything else, so these don't start oscillating anyway. And the 5 chips are all literally just ganged in parallel. And each chip has 2 sections, and they are also just ganged in parallel with 1 sense resistor per chip. So looking at the, if I move this back out the way, looking at this arrangement here, we've got the track that's common to them all, the one that's coming from the LEDs. The bottom LED here comes up and goes right round all these chips. It just commons all these pins together, goes over and then commons all those pins together, and that's where the capacitor's mounted. And it's quite odd because 2 of these pins are just saying no connection. I guess they must be not connected internally. And they've got the 2 inputs, the drain 1 and drain 2 of the 2 sections of the chip. The ground, which is just going straight to the negative here, and the other end of that capacitor, they're just linked together. Basically, it comes up and it must go under the chip and down into that pin. And then the other end of the resistor, the 2 current sense outputs are just ganged in parallel through that 6.8 ohm resistor. I struggled to read the 6.8 ohm resistor because it was partly covered, and also because it actually said 6R80, which is 6.8 ohms. But because it was partially obscured, I couldn't see the whole thing. That's why I was stumbling on reading it earlier on. So that's it. It's 74 LEDs zigzagging down, bridge rectifier, and then these self-current regulating chips with that thermal protection in them, that if they'll pass a certain amount of current based on the value of this resistor, and if they get too hot, then that current will go down. So theoretically, if you got this chip and you just opened it, just operated it, lit it up with just a couple of wires onto it in thin air, and it started overheating, theoretically it should regulate the current down. Whether it would actually do that predictably, I'm not sure if the temperature rose too quickly. I think it should though. So very simple. And the simplicity is perhaps the problem, because they do flicker. I mean, they'd be all right for outdoor floodlights, I'm guessing. Perhaps a weak spot is the fact that LEDs are all in series there, as opposed to the series parallel arrays of conventional, well, let's see if I can focus on this. Let's see if I can, that sort of arrangement where you've got all the series parallel array of chips and the standard LEDs, the power LEDs. So that means if one chip failed and went out, all it would do is just, it wouldn't make much difference to others. But if it went open, then that's the point that, the whole chip would fail. But I don't know how reliable or unreliable these will be. I would say that the 20-watt one is going to probably be more reliable, because the temperature doesn't go anywhere too dramatic. The flicker, that is an issue. That really is an issue, because they don't have the smoothing. It may not have all this complicated circuitry, but it's also missing that smoothing capacitor in input and that smoothing capacitor in output, and that's what ultimately results in the flicker, because it is just basically minimizing the circuitry. But they're interesting. It's certainly a simple solution. I would guess that since these are just so cheap to make, I really don't know why they're selling these for £1.39 at the moment. It seems just too cheap. But because they're so cheap to make and manufacturer looking for the cheapest option, I could see things like street lights and things like that, or outdoor floodlights just using these just because they are so simple. And I wonder, how reliable that would be in the long term. The fact it doesn't have the electrolytics also has the advantage that they're never going to dry out as such. And start causing, one of the common problems of these is the bootstrap diode here feeding the little power supply section, and it just, sometimes you get the problems that these little ballasts overheat and start flashing and pulsing. That's not likely to happen with this one. It's as long as these chips remain relatively stable, and they are designed to operate at high temperature, and they're made by Bright Power, then theoretically it should be okay, but it's always hard to tell. But certainly the 20 watt one is the one I'd choose out of the 20, 30 or 50 watts. I'm not sure how the 50 watt would fare. Maybe the 50 watt just gets hot and then self-regulates down. Much like many of these lights, when you plug them in, they start off bright and high wattage, and then after a while they just start to settle down a little bit. It's an interesting approach. It's certainly a very intriguing LED. That is ultimately the schematic. It's an interesting thing. In hindsight, there's one last little thing. I used a microscope to measure the LEDs by looking at the gel that I'd slit off the thing, and I compared the residue of what was left of the LEDs in it, which were rectangular, to a measuring tape which I held up next to it. And to be honest, they were so small that it was, if the measuring tape, the sort of bands that marked the millimeters were something like that. And the gist was that this was about 0.66 millimeters long, and that was 0.33, roughly a third of a millimeter by 2/3 of a millimeter for the little dice, the actual LED dies on the circuit board. I'm not really sure, is that a standard size? Are they rated, how are these sized? Because I went online, and typing in LED dice doesn't really help, because then you get all the hobby dice, and even LED die, Wikipedia has an entry which shows pictures of them but doesn't actually give you any of the sizing information. You get the ones that say, is it 300 mil or something like that? I'm not sure how they relate to the measurements I got here in millimeters. So maybe you guys can tell me, what would you rate that chip at? Is that a half watt chip? Is that a 1 watt chip? I don't think it's a 1 watt chip. It just seems too small. In hindsight, if that chip was actually being run at 50 watts, where's the calculator? Where's the calculator? There's a little calculator. Bring the wee tiny calculator in again. If it was 50 watts and it was divided by the 74 LEDs, was it 74? I think it was 74. So technically speaking, those LEDs are being run at over half a watt each. They're being run about 0.7 watts. So would that be a 1 watt chip? They just seemed a bit small compared to what I'd normally associate a 1 watt chip being like in appearance. But yeah, I'm not really sure. But I have to say, it was quite fun taking it to bits. It's been a good evening. I don't know if I was shouting earlier on with excitement. It probably was at the beginning of the video, because that was fun to take to bits. That was really interesting to explore. Nothing like I was expecting. It's not like the older versions that used to sort of blow up. So it'll be interesting to see how these actually fare over time.